Okay, so so just to kind of sum up on that last one, copper and copper plus one or copper plus two, both could be a big problem. They could be double exceptions. Also, when you're looking at chromium, right? So chromium is another option, and chromium has all kinds of different charges. But since chromium is already an exception, then like any of your chromiums, whether that's like a two or a three or a five or whatever, any of those values could be a problem. So just watch out for those double exceptions, meaning that the configuration is already a bit of an issue. And so then you have to worry about moving those electrons from the right place. So chromium and copper, just be really, really, really careful when you're dealing with those because they could be an issue. So, okay, last topic right here, ionization energy. Gonna go through this one and then we'll be done. So ionization energy is a trend. It's a periodic trend. And so with the periodic trend, usually there's a pattern for going across the periodic table and a pattern for going down. It's usually a general pattern, but usually can kind of help us out. So what the heck is ionization energy? It is the amount of energy it takes to take an electron away from an atom or an element. So let's say you have something like calcium and you want to turn it into calcium plus 2. Well, that takes energy because you're going to have to remove one electron and then you're going to have to remove a second electron. So every time you take an electron away from an element, it's going to resist because the nucleus is holding on to those electrons. And so you've got your nucleus here in the middle, and it has the positive charge, and it is holding on to these layers of electrons, and these are your energy levels or your rows. And so these electrons are in these layers, and if you're trying to take one and grab it and remove it, then that takes energy. Okay, so every time you take an electron, it takes more energy. So the first one's the easiest, then the second, then the third. Okay, so there's a pattern to this though on the periodic table. So as you go across the periodic table, it's going to increase. So why is it going to be harder to take electrons as I go across the periodic table? Why is it going to be more difficult to take an electron away from fluorine than from carbon? Okay, very, very simple reason. As you go across the periodic table, you are getting close to the most stable elements, which are the noble gases. So the noble gas family, what do they never want to do? They never want to lose an electron. So as you go to the right, you go left to right, you're getting closer to the noble gases. So it's harder to take away electrons from those elements because they're closer to being noble gas and they do not want to give away electrons. Now, if you go down the periodic table, then this ionization energy is going to decrease. And that is because we are going to be getting farther from the middle. So if we're right here at this positive center, and we're getting farther and farther and farther and farther, the farther we get, then that attraction to the middle is going to be less. So as you go down the periodic table, it's going to be a little easier. So I put a minus going down and a plus kind of going across. So, all right. Some general practice here. Example 14. I want you guys to try this on your own. Try to arrange these in order of increasing. So increasing means you want to go from small ionization energy to large. And so kind of organize these. This is always important on a test to make sure you understand if it's increasing or decreasing. So I'm going to pause it here and we'll pick up with the answers on that in a minute. The way to do this is just to go over to your periodic table. There we go. Okay, so let's take a peek here. And let's just rank them. So first one's pretty easy. They were all in the same row. So you've got a fluorine right here, and a nitrogen, and a beryllium. And so that's the order you would put them in. Going left to right, it's going to get bigger, right? We're going towards the noble gases. So it's going to be more difficult to take away electrons as we go. So beryllium would be the easiest, then nitrogen, and last the fluorine, right? We're going to slide across that way. Okay, so let's look at the next batch that they gave us. They gave us beryllium again, and they gave us barium, and they gave us calcium. So now we're going down. So now we're going to be using this trend here. So it's going to get smaller as we go down. So the smallest then is barium, and then the calcium, and last the beryllium, right? So that's what we're going to be doing. Okay, now the last one is kind of a tricky one. You've got phosphorus, sulfur, and fluorine. Okay, so fluorine is the most. So that one's pretty easy, but the other two are kind of tricky. So let me show you this little trick here. And this doesn't come up very often, but here's phosphorus. Okay, this is phosphorus, and it looks like this. And here's sulfur. All right, sulfur looks like this. Okay, there's the sulfur. There's the phosphorus. And that's just their P block, right? So like this is the 3P, and this is the 3P. So here's the deal. Sulfur has an electron to give away. Sulfur can give away this electron right here, and it can still be half full, which if you remember, half full is a little bit more stable. And so since sulfur can give one away and stay half full, and phosphorus can't, then it's a little more difficult to take one away from phosphorus, even though it looks like it should be easier. So it actually is going to go sulfur, phosphorus, and fluorine on this one because the sulfur has an electron to give away and it can still be half full. Okay, so that's kind of weird, kind of different, but it's that half full thing. Not likely to see this on a test, but it is kind of a challenging thing to toss up there. So, all right, we're going to go back and finish up with this last problem, which is how to look at a problem like example 15. Now, the first thing I want you to write down is that there's a question just like example 15 on the test. And so you have to know how to do this. This is on the test. There is no mystery here. So what happens is you're going to have they're going to give you 3 or 4 numbers. And they're going to say their ionization energy. So every one of these is a new electron. So like the 550 is for the first electron. And then the 7500 is for the second. And then this is the third. And this is the fourth. So every time I take away an electron, it's going to cost a little bit more energy. So I write them out, and then I look at my my values, and I ask myself, okay, which one of these has the biggest difference? Okay, not the biggest number, but the biggest difference, right? So I'm looking for the biggest difference. So what we're going to do is we're going to write them out like I did there. And then we are going to subtract the differences in our head or however you want to do it. And we want to just kind of write those down. So I'm going to get a different color pen. Go with the green. I like to go with the red. Okay, so here we go. So this difference here, so 5,550 to 7,500 is a huge difference, right? That's a huge difference. And so these other ones are quite a bit smaller. So like the difference from here to here is only 800. And the difference from here to here is 400. But look at that. Like that difference is massive. And so you want to look at that and be like, man, that is almost 7,000, right? It's like 6,950. That is a huge jump. So what you're looking for is you're looking for the large jump. So what I do is I find that large jump I'm going to erase those, give myself a little more space. I find that large jump, and then I simply am going to identify it. So the large jump happened here between 1 and 2. So the large jump was between the first to the second. Well, the jump was between the first and the second. It meant that you had a noble gas between the first and the second. You had a noble gas here. And here you made it not a noble gas anymore, so it made it really angry. So it went from 5,550 to 7,500. So what you do is you look at this, and then you look at this 1, 2, 3, and 4, and whatever value is the front. So this value is the front between the big jump. Whichever value is in the front, then that is going to be the group that your element came from. Okay, so this had to come from something in the first group, or group 1, or group 1A, and so this had to be something like sodium, lithium, potassium, etc. So it says deduce the group number of the element. The group number would be 1 or 1A. Okay, now let me show you on the periodic table before we run out of time how this looks. So if I take a look here, it came from this first group right here, and what happened is it was something like sodium or potassium or rubidium. What happened, it lost 1 and it ended up over here. But when it lost 2, it left and became a non-noble gas, which it disliked strongly, right? So you lost 1. You lost the first electron, 550. When you lose the second electron, then what happened is it got angry, and that was that big jump of 7,500, because it did not want to leave this column. It did not want to leave the noble gas column. So when you're solving these, look for the big jump, and then identify, okay, it was between 2 and 3, 3 and 4, 1 and 2, and the column is always going to be where that jump started. So going back to this one again, if we would have had the jump, say, maybe the jump was here. Maybe this was 18,700, right? Maybe that was 18,000. If the jump was here, it would have come from column 3, group 3. Okay. So anyway, some things to think about. You've got a homework session here now at the bottom. And so we'll be able to work through that. So